Cambridge IGCSE, May-June 2021, Paper 42. Question 1 Part A. Figure 1.1 shows a sealed weather balloon which is stationary in still air. State whether the overall density of the balloon and its instruments is greater than, less than, or the same as the density of the surrounding air. Here we need to check the density of balloon and instrument and the density of surrounding air are equal or greater than or less than. We just need to compare the density between this balloon and the air. For that we can check this state of the balloon in the air, and it's mentioned it's stationary. It's stationary means it's not floating or sinking. So here we can take the concept of water and ice sinks or float in water. We know that in water ice always floats, and the reason is the density of ice is lesser than the density of water. So the ice sinks. So for any object, its density is lesser than that object will float. So here also you can use that concept. Likewise, if the density is greater, the object will sink. But if the density is equal, the object will not sink or float, but it will be stationary. It will stay in the same place. So here for this balloon and the instrument, it's mentioned it's stationary. So we can understand its density must be equal to the air, density of the air surrounding it. Therefore, the relation between the density of balloon and instrument and density of air must be same. If density is greater than the density of air, the balloon will sink. If the density is lesser than the density of air, the balloon will float. Part B. At night, the gas inside the balloon cools. The pressure of the air outside of the balloon remains same. State whether the balloon rises, falls, or remains stationary. So here we have a balloon which is filled with some gas. When the gas inside the balloon is cooled down or cools, we should understand the kinetic energy of the gas molecules will reduce. So they will start to move with less speed so that the pressure inside the balloon will be less. When the pressure inside the molecules of the balloon is less, the balloon will shrink and its volume will reduce. So because of the less pressure inside the balloon, the volume of the balloon will also reduce. But we know that inside the balloon, even though the volume reduced, the number of molecules is still same. So the mass remains same but volume reduced. So we can check the equation of density as density is mass over volume. And here the mass of the molecules or gas molecules inside the balloon still remains same, but volume has reduced, so that the density will increase. A value at the denominator, when it reduces, the total value will increase, so that the density of the air inside the balloon will increase. So we can write when volume reduces, density will increase. Now the density of the balloon has increased, but the density of the air surrounding is remain constant. So the relation will change now. So now the density of the balloon and instrument will be greater than the density of the surrounding. So now the balloon will sink, because we have already seen when the density increases, the object will sink. So in this question, we need to mention when the density of the balloon increases, what will happen to balloon, whether it rises, falls, or remains stationary. So it will falls. Explain your answer. So since it's 2-mark question, we just need to write 2 points. So we have already seen when the air inside the balloon cools down, its pressure will reduce, so that the balloon shrinks and its volume reduce. So first point we can write volume reduces. So when the volume reduced for the same mass or same amount of gas, definitely its density decreases. So volume reduces and density increases. So these 2 points are enough since it is 2-mark question. Part C, an object is released from the balloon. It starts at rest and eventually reaches a constant speed. On the axis of figure 1.2, sketch a speed time graph to show this motion. So we can describe the motion of this object from the points given in the question, that it's mentioned that it starts at rest. So that the initial velocity of the object must be 0. And next important point is eventually reaches a constant speed. That means gradually the object reaches a steady speed, that is terminal speed. So instead of keep increasing its speed, at one point it reaches a terminal speed or a constant speed. It's because of the air resistance. So at rest, at the beginning, the object is at rest. So at starting position, when time is 0, the speed of the object is at 0. So we should start the graph from 0 point, and at the end eventually the object reaches a constant speed. Okay, so after some time it reaches a constant speed, so it should be a horizontal line. So what will happen in between? So if an object initially it is at rest, when it is falling downwards, we know that at the beginning there is no air resistance or there is no opposing force. So only one acceleration will be there, that is acceleration due to gravity because of its weight. But when it starts to falling down, in between its weight will be acting downwards, but at the same time there will be an upward force, that is air resistance. We can write force due to air resistance. But still there is a net force acting downwards as weight is greater. So still the object speed will keep increase, which will cause its air resistance also to increase. So air resistance will keep gradually increasing, which will cause the object speed to reduce. So, or because of the presence of air resistance, when the air resistance increases gradually, we can write down or we can conclude that the acceleration which is acting downwards will start to reduce gradually, and finally it will become 0. That's why we are getting a horizontal line at the end where acceleration will be 0. But in between this line, the acceleration should decrease gradually because of the presence of air resistance, and it's increasing. So you can draw a line like this. So we should draw a smooth curve. Its gradient should keep reduced as the acceleration is keep reducing, and after some point it should move with a constant speed. That means it should be a horizontal line. So at this part acceleration is reducing. At this part acceleration is 0. That means speed is constant. Here the force due to air resistance must be equal to weight, so that the net force during this horizontal line is 0. That's why acceleration is 0. That's why it has reached a constant speed. But during this section, the weight is more, but force due to air resistance is gradually increasing, so that the net force which is acting downwards also will gradually decrease. That's why the acceleration is reducing or decreasing. So the gradient, because acceleration value we can understand from the gradient. So when the acceleration decrease, gradient or the slope of the graph also should decrease. That's why instead of a straight line, its gradient is reducing, or the slope of this line is reducing. So we just need to draw only the graph, no need to write the explanation here. So only this line is enough. Part 2. State the values of the initial acceleration and final acceleration of the object. So initially when we looking at the object, when the object starts to fall, we know that its initial velocity is 0. So the object has no speed, so no air resistance. So only one force acting is its weight. So the acceleration will be the acceleration due to gravity. That will be g value, that is 10 meter per second square. And final acceleration. At the end of the motion, we have seen the object is moving with a constant speed. If anything is moving with a constant speed, means the acceleration must be 0. Or from this figure we can understand here, force due to air resistance must be equal to weight. So the net force on the object will be equal to 0. So that if the force is 0, definitely the acceleration will be 0. So we can write initial acceleration is 10 meter per second square, where final acceleration is 0. Question number 2. Define the moment of a force. In order to define moment of a force, we can write the equation of moment of force in words. So the moment is force times perpendicular distance from the pivot, where this perpendicular distance is very important. If you are simply writing force times distance, you will not get mark. Part B. Figure 2.1 shows an object of negligible weight. The object is in equilibrium. The object is free to rotate about its pivot P. Calculate the value of force F. So the object is shown in the figure, which is free to rotate about the pivot P, and it's mentioned that the object is in equilibrium. Then we have to calculate the force F. Since the object is in equilibrium, we can use the concept that for an object is in equilibrium, its clockwise moment should be equal to anti-clockwise moment. Now we can check about pivot P, which force cause an clockwise moment and which force cause an anti-clockwise moment. So first we can see which all forces are acting on the object. We don't have to consider the weight of the object as it's mentioned in the question, object of negligible weight. So we can ignore the weight. Now the other two forces acting on the object, one is on the rope as the tension. So this force, that will be the weight of this mass, that is mg, that is 50 times g10. So we will get 500 Newton. So on the rope there will be a force of 500 Newton. We can mention it as tension because it's a force acting on a string. So we can call it as tension. And another force is acting vertically downwards, which is F. This is what you need to calculate. So there are only two forces acting. One is 500 Newton tension because of the 50 kilogram mass, and the second one is the unknown force F, where 500 Newton force will cause a clockwise moment. As you can see about pivot, it will cause a clockwise moment, whereas this unknown force F will cause a anti-clockwise moment about the pivot. Now we can write the equation, that is total clockwise moment is equal to anti-clockwise moment, where clockwise moment is due to 500 Newton force. So we can calculate that moment is force times perpendicular distance. So 500 times the perpendicular distance from the pivot is this distance, which makes a 90 degree to the line of action of force. So this distance make a perpendicular distance, that is 20 centimeters. So 20 times 10 to the power minus 2, that must be equal to total anti-clockwise moment, that is force, unknown force times perpendicular distance. Here the perpendicular distance to the pivot from the force is 12 centimeters because this distance make a 90 degree with the line of action of force. So 12 times 10 to the power minus 2. Since centimeter is at both sides, we don't have to convert. If we convert also, it will get cancelled. Now we can rearrange the equation and make force as the subject. So we will get force is equal to 500 times 20 over 12. And the answer into SF is 830 Newton. So we can write 830 Newton. Part C. Describe an experiment involving vertical forces to show that there is no net moment on an object in equilibrium. You may draw a diagram in the space provided. Here we have to draw a diagram of an object which contains some vertical forces, but the net moment on that object should be 0. Here we can draw a masses on a horizontal bar which is pivoted at the center, and we need to keep masses at both the sides. So we can keep one mass at the left side of the pivot, 1 or 2 or 3, that's up to you because it's not mentioned any measurements. And I'm going to keep same 2 masses in the other side. Now we need to label. So here it's pivot, and this is mass 1, this is mass 2, and mass 1 weight will act downwards, and let the mass 1's weight is 10 Newton. Mass 2, it will be more heavier as it consists of 2 masses. Its weight will be, you need to put a arrow with the double the size of 10 Newton. So it must be 20 Newton, and we need to mark the distance. So let this distance is 5 centimeter. This distance must be 10 centimeter in order to balance the moment. Then only the object will be in equilibrium. Next step, we can calculate the clockwise moment and anti-clockwise moment that are equal. Then only we can prove the object is in equilibrium. So here mass 2 causes an clockwise moment on pivot, about pivot, where the mass 1 causes an anti-clockwise moment about the pivot. So first we can calculate clockwise moment. About pivot is by 20 Newton force, that is 20 Newtons times 5 centimeter, 5 into 10 to the power minus 2. You can even write meter, so no need to convert into meter again. So we will get 100 times 10 to the power minus 2 Newton meter. Likewise, we can calculate the anti-clockwise moment. About pivot, that will be equal to the force of mass 1, that is 10 newtons times perpendicular distance, 10 times 10 to the power minus 2. So we will again get 100 times 10 to the power minus 2 Newton meter. So finally we can write, therefore clockwise moment, total clockwise moment is equal to total anti-clockwise moment. Question 3. Figure 3.1 shows water flowing at very slow speed over a cliff edge. The water falls 15 meters onto the rock below. Show that the velocity of the water when it strikes the rock is 17 meters per second. Here, the water at the top of the cliff will have energy in the form of gravitational potential energy But when the water falls down, all its gravitational potential energy will convert to kinetic energy. So, we can write loss in potential energy must be equal to gain in kinetic energy, or loss in gravitational potential energy must be equal to gain in kinetic energy, where the equation of gravitational potential energy mgh must be is equal to half mv square. So mass is common here, so we can cancel down. And in order to calculate V, we can make V square as the subject. So we will get V square is equal to 2 times GH. Now V is equal to square root of 2 times GH. We can substitute the value. Square root of 2 times G value is 10 times height is given, which is 15 meter. So we will get velocity is 17 meter per second. This is a 4-mark question, where 1 mark you will get when you are writing the loss in gravitational potential energy equal to gain in kinetic energy, and next 1 mark is for writing the equations of gravitational potential and kinetic energy. For the remaining working, next 2 marks. Part B, 30 kg of water flows over the cliff edge every second. Calculate the force exerted by the rock on the falling water. Ignore any splashing. Here we need to calculate the force, where the 30 kg of water in every second. So the mass over time is given, that is 30 kg. Now we have mass over time of the falling water. We can use the equation force is rate of change of momentum, that is mass times change in velocity over time. So mass over time is already given, that is 30 kg per second. We can substitute that times change in velocity is 17.2. That is the answer of previous part. The velocity of the water when it falls is 17.2 in 3SF. Sorry, it must be 17.32. And we will get 520 Newton. So that is the force. Question 4, Part A. Pollen particles are mixed into a liquid. They are seen to move when observed through a microscope. Part 1. Describe this movement. So here we can see how the pollen grains moves in liquid, where this white circle represents the pollen grain. They will be massive or big in size comparing to the liquid molecules, and here yellow circles are molecules of liquid. So as you can see, these fast moving water molecules or liquid molecules, they will be moving randomly. When they collide with these massive dust particles or pollen grains will also move in random direction. So we can describe this motion as random motion. The correct answer is random. Or you can write zigzag, that is also correct. It will be moving straight but not to a particular direction. Part 3. Explain this movement in terms of molecules of the liquid and pollen grains. So we have already seen molecules are small in size comparing to the size of pollen grains, but these fast moving molecules or liquid molecules collide with these massive or heavy pollen particles, and these collisions from molecules are not in particular direction but an uneven collision or collision from different directions cause a random movement of pollen particles. Therefore, we can write down these uneven collisions cause random movement. It's a 3-mark question, and the important keywords are fast moving molecules with massive pollen particles. Massive is also very important. If you write these points, you will get 1 mark. Next, 1 mark for writing about the collision between the molecules and these pollen grains. And the last 1 mark you will get for mentioning uneven collisions cause random movement. Part B. Medical professionals sometimes rub ethanol over the skin of a patient. Ethanol evaporates readily at room temperature and has a high specific latent heat of vaporization. State whether the patient experiences heating, cooling, or neither at the site where the ethanol is applied. Explain your answer. So here when the ethanol applied on the skin, ethanol will evaporate, and for the evaporation process ethanol molecules will takes energy from the skin or takes heat energy from the skin. So the skin will lose some heat energy. So it will result a cooling effect in the skin. So if we are writing step by step the process of evaporation and how it's a cooling process. The first point we can mention here it's evaporation. So for evaporation, the molecules needs energy to escape from the liquid. This is how evaporation happening. And from where these molecules gain energy. So the molecules gain energy by absorbing thermal energy from the skin. So this is how the patient experiences cooling, because the ethanol molecules, in order to evaporate, it takes thermal energy from the skin. Since it is 3-mark question, we should write the answer with 3 important statements. So first statement, we should mention whether it is heating, cooling or neither, and we have already seen it will leave a cooling effect. And we need to give explanation. Therefore, we can write down ethanol molecules takes energy to evaporates. And for these, the thermal energy is taken from the skin. Out of 3 mark, 1 mark is for writing the statement and the 2nd mark for writing the ethanol molecules takes energy to evaporates. You should mention the process evaporation happening here. And the 3rd mark is for writing thermal energy is taken from the skin. Part 2. State any effect on the rate of evaporation of ethanol when a fan blows air over the patient's skin. So when the fan blows air over patient's skin, it will increase the evaporation process because wind is one factor which will increase the evaporation rate. So here we can write the evaporation increases. Question 5 part A. A machine delivers a hot drink in a plastic cup which is uncomfortably hot to hold. Figure 5.1 shows the cup with the hot drink. Figure 5.2a shows the cup with the hot drink and a holder for the sides of the cup. Figure 5.2b shows a cross-section through the holder. The holder is made from 2 strong paper cylinders separated by a wavy piece of strong paper to make air gaps. So there are air gaps present in the holder. Explain how using the holder makes it more comfortable to hold the cup. So the cup consists of hot water. And a holder is also attached to the cup, and the holder consists of lots of air gaps as we can see in the cross-sectional area. Here we should explain how this arrangement or construction of holder will help to hold the cup comfortably. So here the main reason, the holder consists of lots of air in between the space, and air is a bad conductor of heat. So that is the first point we can write. Air is poor conductor. So the holder reduces the conduction. As the holder consists of lot of air in between the gaps. Therefore, the temperature of outside of holder reduces. Since it is 3-mark questions, these 3 points are enough. So even though there is hot drink inside the cup, these heat waves cannot pass through the cup holder, as the holder consists of lot of gaps which is filled with the air, as air is a good insulator or a bad conductor of heat. A student carries out experiments on the cooling of the hot drink described in A with and without the holder in place. He finds that the holder only reduces the rate of cooling slightly. Suggest and explain another action that reduces the rate of cooling more effectively. Here we should mention another method to reduce the cooling rate. We can put a lid to cover the cup in order to reduce the cooling rate. So we can write put a lid to cover the cup. So here we can see what will happen when we put a lid to a cup which consists of hot liquid. Since the liquid is hot, the thermal energy can transfer through convection, that the hot air will rise upwards. So this is one way the thermal energy can escape from liquid to surrounding air. But if we close the cup with a lid, the hot air cannot escape from the liquid, so that we can reduce the heat loss by the process of convection. This is how a lid helps to reduce the rating of cooling effect. As an explanation, we can write down, lid will help the heat loss from the convection. Part C, state the method of thermal energy transfer from a star through the vacuum of space. So there are basically 3 methods for the thermal energy transfer. First one is conduction, second one is convection, and the third one is radiation. But for the conduction and convection, it requires matter. But for radiation, the heat can transfer even through vacuum. One example is we are getting heat energy from sun through the process of radiation, because we know that the heat waves traveling from sun to earth through vacuum space. So here we can write radiation. 6 part A. Figure 6.1 shows a ray of green light passing through a prism. So in the figure we can see a ray of green light when it is passing. Instead of going straight, it deviating, or it gets refracted so that it's bent away from the normal and it takes new path at both the surfaces. A ray of blue light is directed towards the prism on the same path as the ray of green light. On figure 6.1, draw the path of blue light through and out of the prism. So now we have to draw what will be the path of a blue light. If the ray of blue light is initially passing in the same path of the ray of green light, but we can check how much the blue light will refract or deviate from its path comparing to the green light. For that we can look at different colors and how it deviates. So we can consider the colors in Bibjior. So I am writing the colors in order: violet, indigo, blue, green, yellow, orange, red. And when we are looking at the wavelength, we can understand that violet has the least wavelength. So the wavelength is less or least comparing to other colors, and the wavelength will keep increase in the same order, and for the red light the wavelength will be maximum. So out of these 7 colors, red light is the color which has the maximum wavelength, and violet is the color which is having minimum wavelength. So the wavelength will increase in the same order from violet to red. Now in the given question, there are two colors mentioning. The first one is green and its path is already shown. And the second color is blue. So we have to check what will happen to blue. Before that, we can check what will be the amount of deviation or refraction when these colors passing different boundaries. Here we can understand that when the wavelength is less, the deviation will be more. So for any color, if its wavelength is less, it will deviate more. So the deviation will keep decrease when wavelength increases, and we have seen red color is having maximum wavelength, so the deviation will be minimum. So we can say the deviation will be maximum for the colors which are having less wavelength. Now we can look at these two colors mentioned in the question, that is green and blue. And comparing to green and blue, we can understand that wavelength of blue is less than the wavelength of green. So green has a wavelength which is greater or more than the wavelength of blue. So from that we can understand, as the wavelength of blue is less, it will deviate more. This point is very important, that is less wavelength will result more deviation. So from this we can understand that as the wavelength of blue color is less than the wavelength of green color, blue will deviate more from its initial path. So this is a very important relation. So from this we can draw the path of blue light. So initially it's passing through the same path, but once it's entering inside the prism, it will deviate, and the deviation will be greater than the path of green. So it will be bit down. And again when it is passing through the other boundary, it will deviate more. We need to put the arrow to indicate the direction. Therefore, this will be the path of the blue light through and out of the prism. Part B. The wavelength of the blue light in air is 4.8 times 10 to the power minus 7. So the wavelength lambda is given. Calculate frequency of the blue light. Here, in order to calculate frequency, we can use the wave equation, that is speed of a wave is the product of frequency times wavelength. In order to calculate frequency, we can make frequency as a subject, so we will get speed of the light over wavelength, where what is the speed of light? Light is an electromagnetic wave and its speed is constant, that is 3 times 10 to the power 8. Over wavelength is given, that is 4.8 times 10 to the power minus 7. Answer is 6.3 times 10 to the power 14. So 6.3 times 10 to the power 14, unit of frequency is hertz. Question 7. Part A. Figure 7.1 shows two magnets and the gap between the north pole of one magnet and the south pole of the other magnet. On figure 7.1, draw 3 lines to show the pattern and direction of the magnetic field in the gap. Here we need to draw 3 lines. So first we can draw the field line exactly at the center. That should be straight and perpendicular line. The center line should make a 90 degree to these bar magnets. You have to be very careful, and you should put the direction. And field lines will always point towards south pole. So this is the first line you can draw, and the second lines you can draw with a bit deviation. No need to be straight, but the direction should be again towards south pole. Part B. First part. Figure 7.2 is a repeat of figure 7.1 showing the two magnets. On figure 7.2, draw the position of a plotting compass needle when it comes to rest in the gap between North Pole and South Pole. Here we need to draw a compass needle. So we can draw a compass needle where a needle indicates the arrow which will always show the direction of magnetic field lines. So this will always point towards a south pole of a magnet, and this arrowhead of this magnetic compass, we can call it as north pole because it should attract to the south pole. So here when we draw the arrow or the compass, the needle should point towards the south pole and the needle side should be north. The other side of the needle should be south. Part 2, explain why the needle comes to rest in this position. So as we have discussed, the compass needle will always point in the direction of magnetic field. To score 1 mark, we can write compass needle points in the direction of the magnetic field. Because in the previous session, we have already seen the magnetic field line, if we are drawing, it will be pointing towards the south pole. So the needle of a compass will also point in the same direction. It's a 2 mark question, so we need to write one more point. Here we can see the north pole of the needle is attracted to the south pole of the magnet as opposite poles attracts. We can write this point additionally, that the north pole of the compass or needle attracts the south pole of the magnet. Part C, describe a method of demagnetizing a bar magnet. There are two methods. One is by heating or hammering that bar magnet, which should lie magnetically to east-west direction, or by placing the coil or this solenoid with AC, then reduce this AC current to 0. But here we just need to write only a single method. Here we can write heating or hammering a bar magnet which is lying east-west direction. Or I am writing the other method also. Placing a bar magnet in a coil with AC, alternating current, and withdraw or reduce the current to 0. These are two different methods, but you need to learn both the methods when you prepare for the exam. Because in some papers you can see you need to answer both the methods. Question 8, Part A. Two identical radioactive sources emit alpha particles and gamma rays into two vacuum tubes. Figure 8.1 shows two electrically charged plates on either side of the one of the vacuum tube. Write the symbol alpha once in table 8.1 to indicate any deflection of the alpha particle. Write the symbol gamma once in the table 8.5 to indicate any deflection in the gamma rays. So here we have a source, radioactive source, which emit both alpha particle and gamma ray, and we need to check what will happen to these particles when they are passing through the vacuum tube. But there are two plates electrically charged kept at the top and bottom. One is positively charged and another one is negatively charged. So how it will affect the deviation of this alpha and gamma? This is what we need to know. So we can look at the table and we should check what will happen to alpha and gamma gamma ray, whether it will deviate into the page, out of the page, or there won't be any deflection, or towards the bottom or towards the top of the page. Here, first of all, we can think about gamma ray. Gamma ray is simply an electromagnetic wave. It has no charge. Since gamma has no charge, it won't be deviated with these electrically charged plates. Doesn't matter there is a positively charged plate at the top and negatively charged plate at the bottom. As gamma ray is simply an electromagnetic wave, it has no charge, so there won't be any deviation. Therefore, in the table, under no deflection table, we can write it will be gamma. Next one, we need to check about alpha. So we know that alpha is a positively charged particle. So when this positively charged particle is passing through this vacuum tube and when it reaches in between the plate, it will get reflected from positively charged plate and it will get attracted to the negatively charged plate. So the alpha particle will deviate towards the bottom of the tube. As at the bottom there is a negatively charged plate, it will attract the positively charged alpha particle. So we can write alpha in the fourth table that it will deflect towards the bottom of the page. Part 2. Figure 8.2 shows the poles of a very strong magnet on either side of the other vacuum tube. Write the symbol alpha once in the table 8.2 to indicate any deflection of the alpha particle. Write the symbol gamma once in the table to indicate any deflection in the gamma ray. So here it's same like the previous part, but instead of electrically charged plate, here there is two strong magnetic poles. One is north pole at the top and south pole at the bottom. Again we need to check when the source emits alpha particle and gamma ray, what will happen, whether it deflects. If it deflects, in which direction it will deflect. So first we can look at the gamma ray. As we have already discussed, gamma ray is an electromagnetic wave. It has no charge, so that it will not deflect or deviate in any of the electric or magnetic field. So for gamma particle, again we can write no deflection. Now we can look at the alpha particle. Alpha particle is a positively charged particle and it's moving initially towards right, but there is a magnetic field lines in between these magnetic poles and the field lines will be always towards the south. So we have two directions. The first one is the direction of alpha particle and which is moving towards right. Then we have the direction of the magnetic field and which directs towards the bottom of the tube. These two we can understand from the figure. Now we need to check if a positively charged alpha particle is moving in this direction with a magnetic field which is directing downwards, what will be the direction of force experienced on this alpha particle? Here you can use Fleming's left hand rule. So when you are using Fleming's left hand rule, you should keep your three fingers perpendicular to each other as shown in the figure, where the thumb will indicate the direction of motion. This is what we need to check here. So here we have the direction of magnetic field that should be point in the second finger or your index finger. So here we can see the magnetic field that is directing bottom. So this one towards bottom, you should direct your second finger. Likewise, the current should be point with the third finger, and in this given question we know that the current is nothing but the flow of electron in opposite direction. So we can consider the alpha particle's motion as the motion of the current, and for that it should point towards right, as we have seen. So your third finger should point towards right, as it should indicate the path of current or path of alpha particle. So when you point your second fingers to the bottom and third fingers towards right, you can see your thumb directing automatically into the page, so that the motion of the alpha particle will be into the page. So here at the first box we can write alpha. Part B. Figure 8.3 shows a simple direct current DC electric motor with a split ring commutator. State and explain the direction of the rotation of coil as seen from pivot X. So again in this question there is a current. Current is present and a magnetic field is also present, and its direction is from North Pole to South Pole. And here we have to check the direction of rotation. That means we need to understand the direction of motion. So again here we have to use the same concept which we have used in the previous section. We have to use Fleming's left hand rule. So when we use that rule, 3 fingers indicates 3 directions. First one is current, then magnetic field, then motion or force. And the current represented by the third finger, magnetic field represented by the second finger, and the motion or force is represented by the thumb or first finger. And in this given question we have the direction of current and direction of magnetic field. So we have the direction of current and direction of magnetic field. Here we can check what is the direction of current. By looking at the terminals of the battery, we have a cell, a battery with positive and negative terminal, and we know that the current will flow from positive terminal of a cell. So this will be the motion of current and which will pass through this coil. So here the direction is out of the page, and here the direction is into the page. Then it will go to the negative terminal of the battery. Now we can concentrate at this side of the coil. Here the current is, direction of current is out of the plane, whereas the magnetic field direction is towards right. So what will be the direction of the motion? We can again keep our left hand mutually perpendicular to each other as shown in the previous part, and we can use Fleming's left hand rule. So first point the third finger out of the plane or facing, pointing towards your own face. By keeping that third finger out of the plane or towards your own face, now look at the second finger. The second finger should point towards right. Now look at the direction of the thumb. In which direction thumb points? If you keep your third and second finger correctly as discussed, your thumb will be pointing to the top. So when we are looking at the figure, we can understand this side of the coil will move upwards. Now we can look at the other side of the coil where the magnetic field line still indicates towards right, but the current is changed. Initially it was out of, but now you can see the current is moving into. So again we can keep our left hand accordingly, where the magnetic field line, that is the third finger, the second finger should point towards right, but current should point into the plane of the paper or away from your face. Then check your finger, thumb, that will be pointing to the bottom. So the right side of the coil motion will be to the bottom of the plane. So now we can understand that the coil will rotate in this direction, that is in a clockwise direction. Therefore, here we can write, state and explain the direction of the rotation of the coil as seen from pivot X, and we have seen the coil will rotate in clockwise direction. In the statement we can write clockwise direction and the explanation. So as an explanation we can write using Fleming's left hand rule, force on left wire is upwards and force on right wire is downwards. Here on the figure also you can indicate or label the force. Here also you can indicate force which is acting downwards. Part 2. The coil rotates through 90 degrees from the position shown. State what happens to the moment in this position. Let's look at the figure. Now we can see the position of coil in the given figure is in a horizontal plane. When it rotates 90 degrees or 1/4 of a complete cycle, it will become vertical. So not only the coil but this commutator, these split rings will also rotate 90 degrees. That means these gaps between the split rings which will rotate a 90 degree. So the gaps will become or gaps will reach at this plate next to the brushes. So when this coil rotates 90 degree, these gaps will come next to the brushes. So the gaps position will be here. So it will exactly move to this position, that is 1/4 of a cycle. So in the place next to the brush, the commutator's gap will come. Now you can see the commutator and the brush are touching so that the current can easily flow from the cell to the coil. So there is electricity so that it will work. But when this commutator rotates 90 degree, the commutator won't be touching these brushes as the gaps come and contact between the space between the brushes. So during this time when the current passing, it cannot flow through this commutator or split ring through the coil because there is no connection, as there is a gap between the commutator and the brush. Therefore, there won't be no force. If there is no force, it's because there is no electricity or no current passing through the coil. If there is no current, there is only a magnetic field present but no current. So without a current, there won't be any force acting on the coil. So the force will be zero. If the force is zero, moment will be zero because the equation of moment is force into perpendicular distance from the pivot, where force is zero, so the moment will be zero. But even though there is no force on the coil will rotate. It's due to its initial momentum, or due to its inertia, the coil will continue to move its rotation. That's why when the coil is exactly at 90 degree, even though there is no force, the coil continue to move because of its inertia or initial momentum. So here we can write the moment will be zero. We can write the answer in words. Zero moment. Part 3. The coil is rotated through 180 degrees from the position shown. By considering the forces on the coil, explain how the split ring commutator enables the motor to turn continuously. So here it says that when this coil rotates 180 degree, that means half of a cycle. So this right side of the coil will become or reach to the left side, and like right side coil will reach to left side. Likewise, the left side coil will reach to the other side. But still the coil will continue to move in the same way. So again we can look at these split rings. When the split rings rotate 180 degree, this split ring which is now at left side will go to right side, and this split ring which is at right side currently, when it rotates 180 degree, it will go to the other side. So along with the split ring, this coil which is also attached to the split ring will also move to the other side. That is, the coil now staying at the right side will move exactly to the left side, and coil currently at the left side will move exactly to the right side. Now again the current will be flowing from the cell through the split rings and then to the coil, then the other side of the coil, then the right split rings, again back to battery. So still there will be a flow of current. So because of the presence of current and magnetic field in the coil, there will be force. So the coil at the left side, the current is passing out of the page, so that the force will be exactly as we have discussed. The force will be same as what we have already checked before. On this left coil, force will be again upwards, and on the right coil the force will again act downwards, because even though current in the coil reversed or changes the direction, the forces on the wires in new position still be up on the left and down on the right. So hope it is clear. I will give one YouTube video link for the animation of this explanation, so it will be easy for you to understand the concept or working of this DC electric motor. So here we can write current in the coil reverses, which we have already seen because the coils will turn exactly to the opposite sides. But forces will be still on the same direction. Or we can write forces will be still acting upwards on left coil and down on right coil. So for the complete coil, the rotation will be same and it will continue to rotate in the same way. 9 part A. Figure 9.1 shows a circuit. On figure 9.1, draw two clearly labeled arrows to show the direction of the electron flow and the direction of the conventional current in the circuit. So first we can show the direction of the electron flow. Initially we need to look at the terminals of the battery, where the right side in the given battery it is negative terminal and left side it is positive terminal. And the negative side of the cell or battery, as the name indicates, it will have negatively charged particles, that is electrons. So these electrons will move or repel from negative cell side of the battery, or the free electrons present in the conductor will be get repelled from the negative side of the battery. So the electrons will always move from negative side of a battery to the positive side. So that will be the direction of electrons. So here we can put the arrow that this will be the direction of the flow of electron from negative side to positive side, and we need to indicate it as electron flow. But the direction of conventional current is always opposite of the direction of the flow of electrons. So in this circuit, electron is flowing in clockwise direction, so that the conventional current flowing we have to consider in anti-clockwise direction, or it will be always from positive side of the battery to the negative side. So we can put an arrow directing in an anti-clockwise direction, and label as conventional current. So here flow of electron is clockwise direction from negative terminal to positive terminal, and the flow of conventional current is in anti-clockwise direction. Part B. The current in the motor is 13 ampere. The charge on the electron is 1.6 times 10 to the power minus 19 coulomb. Calculate the number of electrons that pass through the motor every second. So every second means time is 1 second, or in 1 second time we need to calculate the number of electrons that passes through the motor, where the total value of the current which is passing during this time is given, which is 13 ampere. So we are provided with the current that is 13 ampere, and charge of one single electron we can represent it with small q, that is 1.6 times 10 to the power minus 19 coulomb, and time is also given 1 second. Here we need to calculate the total number of electrons. We can represent it with capital N, that is the total number of electrons flowing through that motor in 1 second, which we need to calculate. So in this question we need to know that if we have a conductor or motor, whatever, we need to calculate how many number of electrons are flowing in 1 second. And the charge of one electron is given. The charge of a single electron, that is 1.6 times 10 to the power minus 19 coulomb. And if there are n number of electrons, what will be the total charge of electrons flowing? The charge of a single electron is 1.6 times 10 to the power minus 19. If there are total n number of electrons, so the total charge of all the electrons, which we can represent with capital Q, will be the total number of electrons times charge of a single electron. So this is the equation to calculate the total charge flowing in 1 second Q. That is total number of electrons flowing times charge of single electron. Now we can use the equation of current. Current is rate of flow of charges. So I is Q over T, where Q is the total charge flowing in the given time, and the Q equation we have already mentioned in terms of number of electrons times charge of single electron. So Q, the total charge Q, we can write total number of electrons times charge of a single electron over time. Now in order to calculate the total number of electrons, we can make capital N as the subject. So we will get number of electrons N is equal to I times T over Q. So I is given, that is 13 ampere, times time is 1 second, over charge is 1.6 times 10 to the power minus 19. And the answer is 8.1 times 10 to the power 19. Since it is simply the number of electrons, there is no unit. Question 10 part A. Figure 10.1 shows the potential difference current graph for a circuit component K. Calculate the resistance of the component K when the current in it is 4 milliampere. So we need to calculate the resistance R. We can use the equation resistance is equal to voltage over current, and we are provided with a graph. And the current value I is also given, that I is 4 milliampere. So we can find when the current is 4 milliampere, what will be its corresponding voltage. So we can check that by extending at 4 milliampere current, what is the voltage. And its voltage value is 9.2 volt. Therefore we can substitute voltage is 9.2 over current is 4 milliampere. So 4 times we need to convert milliampere into ampere. For that we should multiply 10 to the power minus 3. Milli means 10 to the power minus 3. So we can substitute that instead of milli 10 to the power minus 3, and the answer is 2300 ohm. Part B, figure 10.2 shows a circuit containing component K. So this is component K. By looking at the symbol of component K, we can understand this is a thermistor. At low temperature, component K has a much greater resistance than resistor R. At high temperature, component K has a much smaller resistance than resistor R. State and explain the effect on the lamp when the temperature changes from very low to a very high. So when the temperature changes from low to high, we need to check how it will affect the working of lamp. So at low temperature, this resistance of this component, that is thermistor, we have seen resistor is very high. So when the resistor is high, what will happen to the voltage across this component? We need to check that. So as the temperature is low, as mentioned in the question, the resistance will be greater than resistor R. So in this case, what will happen to the voltage across this thermistor or given component? So here very important point you need to know in order to answer this kind of questions are, when the resistance of any component increases, it will consume lots of energy to work. Therefore, the potential difference across that component or the voltage consumption of that component will be high. So this is a very important point you need to remember always, that when the resistance of any component is greater, its potential difference across that component will be greater. Therefore, using this concept, here at low temperature, as the resistance is greater, the voltage across this component will be greater comparing to the voltage across the resistor. So here the voltage will be less, and this same voltage is sharing with the lamp because they are parallel connection. So as the voltage across resistor R is less, the voltage across the lamp will also be less because lamp and resistor R are connected in parallel. Therefore, at low temperature, we can conclude that as the voltage across the lamp is less, the current in the lamp will be less, and therefore the brightness of the lamp will be less. So this is what happens when the temperature is less. But from a low temperature to high temperature, we can see what will happen. At high temperature, just opposite will happen. At high temperature, the resistance across the component will be less, so that the voltage across the component K also will be less using this concept. Therefore, the voltage across resistor R will be more, so that the resistance across the lamp will be also more. As the resistor R and lamp are connected in parallel, the voltage across both resistor R and lamp will be same. So here we can see at high temperature, the voltage will be more across the lamp, so that the current will be more, so the lamp glows. Refer to voltage at X in your explanation. We need to state and explain the effect on the lamp when the temperature changes from low to very high. So we have seen when the temperature changes to high, what will happen here. So we need to write this, but we should mention about the voltage at point X. Voltage at point X will be same as the voltage across the voltage across the lamp. So we can write at high temperature. First we need to write the statement. Statement is the final result, and we have seen that the light glows. So we can simply write light glows. And as an explanation we have to write the reasons. So at high temperature, or when the temperature increases, the resistance across the thermistor or across the component K thermistor name is not indicated in the question, but we should understand by looking at the symbol. So you can mention as thermistor. The resistance across the thermistor reduced. Therefore, the resistance of the resistor R increases, but we don't need to mention that. But because of that, the voltage across resistor R increases. Or even you can write potential difference of point X increases. So high voltage across the lamp. When the voltage is high, current also will be high. Therefore, we can write down larger current in lamp. Part C, state the name of the component K. We have already discussed about it. It's a thermistor. By looking at the symbol given in the figure itself, we can identify its thermistor, and the property of this component is also mentioned in the question, that is when the temperature is high, resistance will be low. When the temperature is low, resistance will be high, so that we can understand easily that this is a thermistor. Question 11, Part A. A student investigates a radioactive substance in a laboratory. Figure 11.11 is a graph showing the count rate detected as the substance decays for 7.5 minutes. In this question, we are provided with a count rate time graph of a radioactive substance. The background radiation is 20 count per minute. Determine the half-life of the substance. So we can check the count rate when time is 0. So at the beginning, the count rate is 220. From this value, we can calculate what is the initial count rate from the substance without background radiation. So here we can find initial count rate without background radiation will be the total count, that is 220 minus background radiation. So 200 is the original count rate from the radioactive substance at the beginning. Now we can check what will be the count rate of the substance after half time. So count rate of radioactive substance after one half life will be half of its initial count, that is half of 200, 100. But the total count rate after one half life will be the count rate of the substance plus the background radiation. Background radiation will be always 20. So the total count rate will be 120 after first half life. Now we can look at the graph and check what is the time when the count rate is 120, which will be the half life. So we are going back to the graph, and 120 is this point, and the corresponding time is 2.4 minutes. Therefore, we can write half-life is 2.4 minutes. This is a 3-mark question. For finding out the initial count rate without background radiation, you can score 1 mark. And second mark for finding out the total count rate after one half life. Then the final mark for finding the half life from the graph. Part 2. Calculate the count rate detected at time 9 minutes. So we can check how many half lives have gone through within 9.6 minutes. So the number of half lives will be is equal to the total time over the half life, that is 2.4, and that is 4. So now we can check after 4 half lives what will be the count rate. So the count rate will be, initial count rate was 200. After one half life it will be half of that value. Second half life again half of the value. Third half life again half of that value. And fourth half life again half. So you have to multiply 4 1 by 2's. So the count rate from this radioactive sample will be 12.5 after 4 half lives. But the total count rate, we have to consider the background radiation also. So the count rate from this sample plus background radiation, that is 20, we will get 32.5. So into SF we can write 33 counts per minute. Part B. The substance emits alpha particles and gamma rays. The student suggests that it is safe to store the substance in a plastic container of thickness 2 mm. State and explain whether the student's suggestion is correct. So we just need to check keeping these alpha particles and gamma rays in a plastic container of thickness 2 mm is safe or not. So when we look at the penetration power of alpha particle can be stopped or absorbed by even by a paper. Therefore, we can keep alpha particles in a plastic container. Even keeping it in a paper is safe. But when we are looking at gamma rays, as you can see, gamma rays can penetrate and pass through paper, plastics, even steel, and it can reach to lead. But lead is the metal which can stop the penetration of gamma rays. That means gamma rays cannot be stopped by using a plastic. So keeping gamma rays or a radioactive element which produces gamma rays in a plastic container is not safe, as these gamma rays can penetrate through the plastic container. Therefore, here this statement or the student's suggestion is wrong or incorrect. And we need to give the explanation. As an explanation, we can write initially, gamma rays are dangerous and the plastic container is penetrated by gamma rays. Thank you for watching this video. If you find this video useful, please like this video and subscribe my channel. Thank you.